Hey everybody, welcome to Chapter 5. We're going to take a look at 5.1 in this video, and you should know that we're only about 6 or 7 sections away from completing the entire class. So we've got plenty of time here. We're going to probably do one section each class period. I'll release one section on every Monday and Wednesday for the next few weeks, and then we'll be able to review and take the Chapter 5 test, and then we'll do a good review for the final exam also, and we'll take that final exam at the very end of April, very beginning of May. But I think that you should have plenty of time to kind of practice this and digest it and ask me questions, email me questions, reach out to other people on Facebook, in our Facebook group, and do whatever you need to do so that you feel really comfortable with this material. But keep working hard, keep it up. I know this is kind of strange how we're learning in this type of a format now, but I'm hoping it works for you guys. And like I said, just continue to always keep those communication lines open with me. Okay, so the indefinite integral. Basically what we're going to start doing here is we are going to start taking antiderivatives. And so instead of starting with a function and finding its derivative, we're going to be starting with a function and kind of going backwards and figuring out what was the original function that led to this function, which now represents a derivative. So this is the inverse operation to differentiation. And eventually we're going to call it integration. And even in this section, I refer to it as the indefinite integral, but you should know that it goes by a whole bunch of names. And so sometimes you'll hear me refer to this process as computing an indefinite integral. Sometimes it's finding an antiderivative, different things like that. So I'll break this up into a couple of different videos for the notes. I'll also do a video for the exit problems that we would typically do at the end of class. Okay, so some notation. Before, whenever we did derivatives, remember how we would say, if we were computing a derivative, we would say the derivative of a function would be f prime of x. Well, we're actually going to continue to see that notation, but we also start to see some other notation, because sometimes, like when we were doing the derivative of a function, we knew that we were starting with our function f, and we therefore said the derivative of f would be f prime. But now when we're starting with our function, we might not be doing a derivative. We might be interested in saying, what is the antiderivative of that? And we need to talk about ways of finding that antiderivative. And so you're actually going to see, instead of f and f prime, sometimes you're actually going to see a lowercase f and a capital F. And capital F represents the antiderivative of f, or the function that when you take its derivative leads you to lowercase f. So you'll see notation like this. Instead of me saying what I set up here, I can state this. I can say the derivative of capital F is equal to lowercase f. And a lot of times that's because we're starting with lowercase f. And typically the way that we write this is like you see right here. The antiderivative, that's what that means, or the indefinite integral of f of x, and this stands for with respect to x, is equal to capital F of x. So this is saying the function that has f as its derivative is capital F. Okay, so hopefully you can get used to that notation. The function that has lowercase f as its derivative is capital F. And we say that the antiderivative of lowercase f is capital F. The symbol here that you see is actually a stretched out S, and I'll talk more about that in the next video, or in the next section. But essentially, when we deal with indefinite integration, we're dealing with a summing process, and I'm not going to say anything more about it right now, but this quite literally is a stretched out S, and you'll see that a few videos from now. Okay, so to be technically correct, when we do an antiderivative of lowercase f, we don't want to just stop and say capital F, because technically if you added any constant to capital F, then this could be the antiderivative of lowercase f. And the reason is when you take the derivative of capital F, you get lowercase f. And when you do the derivative of a constant, you get 0. And so no matter what constant you attach to capital F, when you do the derivative of this, you get back to lowercase f. So you're going to see me consistently putting in a plus c in a lot of the examples that I go through in these notes. In this notation, this right here, this symbol, like I said, is just like a stretched out s, and it stands for the indefinite integral or the antiderivative. But f of x is called the integrand, and dx is called the variable of integration. This will take on a little bit more meaning when we talk about areas in section 5.2, but right now, when you look at this, you really don't even pay too much attention to dx other than noting that the variable that we're working with here is most likely in terms of the variable that this is right here. So if this was a function of t, then this would be a dt. If this was a function of z, this would be a dz. And like I was saying, there's all kinds of names that this goes by. So finding the indefinite integral of f of x is called finding an antiderivative. It's called evaluating an indefinite integral. It's called finding the solution to a differential equation dy over dx equals f of x. Those all mean literally the exact same thing. So when I give you a question, I say find the antiderivative. It just means find the function that has our particular function as its derivative. Or if I say evaluate the indefinite integral, find the function that has this as its derivative. Or find the solution to the differential equation, I quite literally mean, once again, to do exactly this. We'll talk about a visual way to kind of think about the solutions to these on the next page, or probably a couple videos from now. And the other thing is, when we're going through this, I strongly encourage you to kind of review your rules for derivatives, because there's going to be a strong connection to your rules for antiderivatives. And there's also the table that I think I've given you guys a copy of that in class, but it's in the ebook. I think it's one of the first links that you see in the ebook. And I said here I suggest memorizing all of these antiderivatives. Not right now. We're not going to memorize all of these, but I would try to be very familiar with them. Maybe have some note cards, or have that chart handy, that table handy when you're going through a lot of these problems. So here's a few that you would see from the table. This basically says what function has 1 over x as its derivative. Well, that function is the natural log of x. But in this case, to be technically correct, we need to say the natural log of the absolute value of x. And the reason is, in this context, there's no restrictions on x. And so we're thinking, okay, well, we know natural log of x had 1 over x as its derivative. But now we need to ensure that when we're doing the natural log of a quantity, that is a positive quantity. And again, to be completely correct, we also need to put in a plus c right here. So this is the antiderivative of 1 over x. In this one, if you have the antiderivative of a to the x, now recall that the derivative of a to the x, when we did the derivative of a to the x, it was a to the x times the natural log of a. So when you do the antiderivative, it's actually going to be a to the x divided by the natural log of a plus c. And the reason is, I always check things. And the cool thing with antiderivatives is you can always go through this checking process. You can say, let's do the derivative of this and see if we get back to where we started. The derivative of a to the x is a to the x times the natural log of a. So the natural log of a's, your constants, would cancel, and you would just get back to a to the x. Or like in this one, the derivative of natural log of absolute value of x, just 1 over x. Okay, this one right here. What function had negative cosecant squared x as its derivative? So there's a trig function that when you do the derivative of it, it gives you negative cosecant squared of x. And that function was cotangent of x, and then we'll say plus c. Okay. Sine of x. Now we remember the derivative of sine of x was cosine, but we want the antiderivative of sine. So what function, when you take its derivative, gives you sine? It's actually not cosine, because cosine of x had a derivative of negative sign. So what do we need to do to this to ensure that when you do the derivative of it, you get a positive sign? That's right, you put a negative in front. So the derivative of negative cosine of x is negative of negative sine of x, and it gets you back to sine of x. So all of these things that you see right here, the solutions to these antiderivatives, are the functions that when you differentiate them, when you take their derivatives, get you back to the integrand, get you back to what's inside that integral. Okay, let's take a look at a couple of other examples. In these examples, we're going to focus on the power rule a little bit, and this time it's going to be a power rule that we develop for antiderivatives. So for this, for instance, I see this as x to the 2/3 power. And so with derivatives, do you remember how we would bring this number in front? We would subtract 1 from the exponent. Well, if we subtracted 1 from the exponent with derivatives, then with antiderivatives, what are we going to do with the exponent? We're going to add 1. So the antiderivative of x to the n, this is going to be one of the biggest rules. It's going to be x to the n plus 1 divided by whatever that n plus 1 is. And the reason is, when I take the derivative of this, the n plus 1 would come down to the front, cancel with the n plus 1 down here, and then you would subtract 1 from your exponent to get back to x to the n. And so when I get something like x to the 2/3, I add 1 to the exponent, so that gives me x to the, what is that going to give me when I add 1 to 2/3? 2/3 plus 3/3 is 5/3. And then I could divide by 5/3, but instead of writing divided by 5/3, I sometimes like to just do this. Let's put 3/5 in front. Notice if I put 3/5 in front that it's the same effect as dividing by 5/3. And that way, if I took the derivative of this, the 5/3 comes in front, cancels with the 3/5. You get x to the, you subtract 1 from the exponent, and you're going to get x to the 2/3. So that would be my solution here. Or in question 2, this is a tricky one because we've got a product. And we saw before when we did derivatives, there was a product rule that we needed to follow. And eventually, you're going to learn some specialized rules for doing antiderivatives, but we're not going to focus on those here. Our goal in a lot of these right now is to try to get the integrand looking like something that we've worked with before, or get the integrand to somehow involve powers of x. And so in an example like 2, the antiderivative of all of this, I would rewrite it based upon doing a product. I would FOIL all of this out. 1 times 2 is 2. 1 times a negative x is a negative x. X squared times 2, 2x squared. And then minus x cubed. Okay, and that's dx. So the antiderivative of 2 is 2x, because 2x would be the function that when you take its derivative, you get 2. The antiderivative of negative x to the first, it's going to be negative x squared, although when I put that exponent up there, remember when I bring this down, you're going to have to also divide by 2 to get that 2 when you bring it down to cancel and just get you x to the first. So get really comfortable with the fact that the antiderivative of x is x squared over 2. Or the antiderivative of x squared, as you see here, watch how I do this. I leave the 2 there. The antiderivative of x squared, x cubed over 3. The antiderivative of x cubed, x to the 4th over 4. If I said to you, what's the antiderivative of x to the 7th? It would be x to the 8th over 8. If I said, what's the antiderivative of x to the 10th? It would be x to the 11th over 11. So get really comfortable with applying this idea right here. Okay, I'm going to stop this video now. Let's pick up with these other examples in the next one.